In this video I am going to build my biggest floppy music setup to date. In case you don't know my history with floppy music, let me give you a short summary, as this is how I got into YouTube and building stuff in the first place, so this project is quite important to me and takes my floppy music journey to its conclusion. Floppy music in general is simply making music using old floppy drives and sometimes other hardware like hard drives. And you have probably seen other videos with that concept at some point if you are watching this. A simple setup could be built with just an Arduino and a few old drives, making it a great beginner project for a weekend. For that, I want to give some credit to the open source project Moppy from SemiIM, which is how I started my first experiments and videos in 2012 as well, just for fun. Later, after some of the pretty badly recorded videos got quite a lot of publicity for some time, I continued to improve my setup and recordings over the years and made my own implementations with simpler and more reliable native MIDI communication. In the later years, instead of just uploading even more cover songs to YouTube, I went to live events like maker fairs with my suitcase setups. So a nice visual presentation and some interactivity will be important for this new build as well. The massive setup in this video was planned over several years, and I had quite a few different concepts for how to achieve it. After I finally acquired enough drives to make it happen, that's where this video begins. Every drive requires a step, direction and an optional enable pin. So this means for 64 drives, 192 pins, and the controller has to be able to generate very accurate high-frequency signals for each drive. It is clear that a single Arduino would not be up to the task anymore if every drive should be individually addressable. One option would be to use a very high pin count FPGA and a central MIDI controller for really low-level high-speed signal generation, and directly connect each drive to the output pins of this central controller. That would surely be more than powerful enough, so I got a Cyclone 4 EP4CE10 with 164 pins, and this board was quite cheap at the time. The issue here is that it's quite difficult to expand later, as those chips are now very expensive again, with over $300 sometimes, and every drive would have to be connected to a single device. And if I want to control the enable pin as well, it would also require a third pin, which would have to be connected to shift registers, as this one wouldn't have enough pins for that. Instead, now to finally make this project happen, I decided on the very modular and slightly overkill approach to have one addressable microcontroller per drive and connect them to a single bus and a central MIDI controller. Every drive will have a low-cost small microcontroller like this STM32G030 mounted directly to its interface and connected to each other, instead of having a massive amount of wires going to a central point. So let's take a look at how I want to generate the step and direction signals for the floppy drive. I want to use hardware timers in this case. Then I can do it without wasting any CPU cycles. Timer 1 is now used for generating the steps. I have enabled the PWM output channel 1 on timer 1, which is the PB0 pin. And we have a counter period of 64,000. This should be a period of exactly 1 millisecond. And a pulse width of 5000. And of course, a drive has 80 tracks, so we need to count the amount of steps. And after 80 steps, we have to toggle the direction pin. Normally, we could do this in software with an interrupt, but we could make it even more efficient by using timer 3 and using the trigger output on update event. This is an internal line which sends a signal every time this timer overflows, and this can be used for timer 3, which is set in external clock mode, with the internal trigger 0, which is the output from timer 1. Every 80 steps it will toggle the output of the direction pin once. And checking out the scope, now we are at pretty much exactly 1 millisecond, and the direction is also toggling at 80 milliseconds. So I'm currently making a little test setup. Even if I set a breakpoint, the timers would still run and create the back and forth motion. And I can show you this when I just set a breakpoint here and stop the CPU. Now it's stopped and it's still running back and forth, just not incrementing the frequency anymore. And when I continue, the frequency is getting higher again. The address is not hard-coded in firmware, but determined at startup by counting pulses on a chained ID pin. I have now connected the Raspberry Pi Zero via USB in MIDI USB gadget mode to my PC and wrote a simple Python script which just takes MIDI messages, parses them into node on, node off, and pitch wheel, and then can send out over the temporary protocol I've implemented, which pretty much only takes a frequency and a channel, and sends this out via SPI. And you can see on the oscilloscope that it actually receives the SPI data. And yeah, you can see that the SPI clock somehow fluctuates quite a lot, and it's not really the clock speed I have actually set.
6 months later.
I ended up not actually using the Raspberry Pi Zero because the performance was just not good enough for accurate timing. Instead, I'm now using the STM32 based OpenFF board, and in the next scenes I will also use a custom controller board. Because this project requires so many individual controllers, I need to thank JLCPCB for being a sponsor of this project and providing 5 whole panels of partially assembled boards. For simple projects like these, all components were in stock in their warehouse, and common parts often don't even cost any extra setup fee, making full assembly often easier and cheaper than buying parts separately and hand soldering them later. Of course, for more complex jobs, components can be sourced externally as well. If you also need PCBs for your project, check out JLC PCB and get coupons for up to $54 off for new customers, and additionally $24 off for assembly jobs each month for existing accounts. Now, unfortunately, I was not able to get the correct angled headers at the time of the assembly order, so what followed was a whole day of soldering them manually. I am not going to force you to experience that yourself in total, so let's just fast forward to the next step. In the next scenes, I'm using a slightly older version of the controller, but the functionality is the same. In the end, the communication is handled with a half-duplex SPI bus with 4 chip select pins and up to 254 drives per CS pin with our own address or listening if the CS pin of the block is low. The protocol contains a command byte and address byte, 4 bytes of data, and a CRC8 checksum to detect transmission errors and ignore faulty packets. The more controllers are connected, the lower the reliable SPI frequency gets, which is to be expected. In the first tests with just 8 drives, I was able to get up to 10 MHz, while with the full 64 drive system and all the long cables, I had to drop down to about 2 MHz, which is still more than fast enough for music, and I am also using a few tricks to make the transmission more efficient and broadcast to multiple channels at once depending on the layout. So at the moment I'm working on the node distribution function, which will split playing nodes into separate drives. If you don't know, MIDI has 16 channels, but every channel can usually play multiple notes at once. With the old suitcase setup, every drive corresponds to a MIDI channel that can only play one note at once. That required me to manually split polyphonic channels and map them into separate drives. So this would be a file which would be usually played on the old suitcase setup, and every channel only has one note playing at once. Here you can also see a graph of how the MIDI channels were mapped to the drives. On the right side, we had the channels 1 to 8, and on the left side, 9 to 15. Channel 16 was unused, and channel 15 was the HDD. So this also required some special handling to have higher notes, like a voice track on the HDD. The new setup will have 64 drives, which are completely individually addressable. This allows me to be a bit fancier than just duplicating notes. My goal here is a setup that still uses separate channels to target specific drives, but each channel also has 4 drives that can be used to modulate the volume or play multiple notes at once. In this graph you can see 4 different ports, and each port contains all 16 channels. Because all the ports share addresses but have separate chip select lines, sending the same note to multiple ports can be done very efficiently by just enabling multiple ports at once. That would make volume modulation very easy. So at full volume all 4 drives play, at half volume only 2, and so on. If multiple notes play at once or a different distribution function is used that doesn't share addresses for channels, this of course does not work that easily, but I'm implementing in a way to make use of this grouping automatically. So if possible, it will be used. The distribution I'm planning to use at the Maker Faire will likely share 8 channels with 4 drives each on the ports 1 and 2, and the other 8 channels on the ports 3 and 4, so I can have 2 separate blocks of drives on the left and right for a stereo effect like on the old suitcase setup. Here you can see that it will still allow for broadcasting on 2 ports at least, so it is still a bit more efficient than just sending each update separately, but we still need to send at least 2 packets for each channel update. So at the moment for this test I have set the 16 test drives up in 4 channels with 4 drives each. And let's check out how the volume modulation works. Each one of these notes is playing at a higher volume than the previous note. So let's play this and take a look at how many drives are playing for each note. And yeah, as you can see and probably imagined, depending on the velocity, the amount of drives playing this note changes. So this means we have 4 levels of volume available when only one note is playing at a time in this mode. But there's also the option to play multiple notes at once when we have more drives per channel. So the first 4 notes are playing at a high volume, and the second 4 notes are playing at a low volume each. So let's take a look at how many drives are playing when multiple notes are played at once, depending on the volume. When we have one note playing at a high volume, it's like in the previous test, all 4 drives are playing it. When 2 notes are playing at a high volume, then they are played by 2 drives each. With 3 notes, we have them play on 3 drives. because it is not divisible evenly by 4. So the fourth drive in this case doesn't do anything. Maybe I will change this behavior, but this is how it's currently implemented. And with 4 nodes playing, of course, then all 4 drives are playing a different node. And with a low volume node, then yeah, each node is played by 1 drive. First node plays on 1 drive. Then with the second node, second drive plays the second node. Third node is then played on the third drive. And fourth node is played on the fourth drive, so that all 4 nodes are playing at the same time on 1 drive each. Well, actually, the last node is always played on the first drive in the chain. So this always takes priority, the first drive with the newest node. So this means that the latest node is always playing, even if there are fewer drives. So this would be the same if you had just 1 drive, then the last node would be buffered and it goes back to the last node. This was how it was implemented with the old floppy setup. Just now we have a depth of 4 nodes instead of just 1. For stiffening, I've decided to use some 20 centimeter threaded rods diagonally in the towers. And when I use some angled feet, this would also allow me to set a specific angle in the whole tower for better presentation. Another challenge is powering all these drives. These are 64 drives and they might take up to 500 milliamps each, which would result in 32 amps or 160 watts for the whole system. The towers will be split into 2 groups of 4 towers with 8 drives each. So I wanted to use 2 power supplies and I chose to use these Meanwell MDR65, which can supply 10 amps each. And this will likely be fine when we calculate at a more reasonable estimate of about 300 milliamps per drive, because it is very unlikely that all the drives will take 500 milliamps and step at their worst frequency all at once for an extended period of time. These power supplies are also not using a hard overcurrent shutdown, but instead will gracefully limit the current by reducing the voltage in small overload conditions. So this will likely not cause the system to shut down even if there is a current spike for a short time. I am going to mount these power supplies in these 3D printed brackets, which are shaped like a DIN rail, and these will go then under the lowest drive of 2 of the towers, and they will slide in like this, and then I can directly connect the 4 towers directly to this power supply. And these also have 2 terminals, each for the positive and negative, so this should allow me to connect the tower separately to keep the amount of drives per string of wire as low as possible. Because I also need to flash all the 64 controllers individually with the same firmware, I made a pogo pin probe for the programmer and a script which periodically polls the programmer and tries to flash the firmware. And on success, it will wait 5 seconds, so it doesn't flash the same board again. And yeah, this really makes flashing these boards much faster and easier. The controller PCBs plug directly into the header at the back of the drive and are connected with the previously made ribbon cables. The drives are then powered with standard 4-pin Molex splitters, one 3-way splitter, one 2-way splitter, and 4 2x floppy power connectors. And of course this has to be repeated for all of the 8 towers. I won't show you that because it is the same as I'm currently showing you. Initially, when assembling the towers, I did not test the drives beforehand, and it was clear that some of them may be defective or require 12 volt to function. Most drives only need 5 volts, but some older ones, they do need 12 volts, and I had the suspicion that it might be true for some of the older ones, I think these. And when we enable all the drives, we can easily see this. Now, all the LEDs should be lit up, but we can see that this drive, these two, and this one are not enabled. So these do not turn on with these controllers and only 5 volt supplies. So I will need to replace them with newer drives which operate at only 5 volts. I've replaced the drives which were not working before, and I also decided to make this tower fully black because there were 3 mismatched silver ones and I had additional black ones. And when we enable them now, as we can see, all of them are turning on at least. So we are ready to do a all-channel music test now. At events like Maker Fairs, people love to play the drives with a keyboard. This requires splitting the notes from a single channel into all available channels for best volume dynamically. For this system I added a single channel input mode which distributes the notes into all 16 channels independently of their incoming channel, while also retaining their velocity value. For example, I can also play a single note at 4 volume steps, or multiple notes at once, with each of them keeping their volume. Even pitch bends still work and are applied to all channels in this mode. As all drives can be addressed individually, it is possible to create patterns with the enable LEDs too. And lastly, because it's mainly a MIDI instrument, let's hear the system in action with a fully recorded song edited with multiple channels. See how the drives respond to notes with varying volume, activating more or fewer drives at once. thank you to everybody watching and supporting my projects, and maybe you can see it live at the next Maker Fairs.